let me tell you about the agenda, right? So we will be starting with the TCP IP networking, the fundamental of Ethernet LANs, the wide area networks, IP routing, and analyzing Ethernet LAN switching, the Ethernet virtual LANs, the VLANs, the spanning tree protocol concepts, right? Then IPv4 subnetting, classful IPv4 networks, subnet mask, configuring IPv4 addresses, the static routes, how you can configure. So all those things, some of the things are there that are practical as well. So wherever it is possible, I'll give you the practical approach also, that how you can perform these things practically, right? So if something we can do in the router, we can will perform that in the router as well, right? So that's how we'll be approaching for our course. So let's start our session with the very first topic, introduction to TCP IP networking. Now when we are talking about network, guys, right, can I say that when two devices are minimum two devices are communicating with each other, that is a network? Now I'm not going to that definition where I say that uh, it's a combination of like billions of devices communicating with each other. Yes, that is. But if two devices are communicating with each other, can I say it is a network? Yes, perfect. So minimum two devices communicating with each other is a network. Now network can be of between two devices inside the same room as well. It can be between two devices who are communicating over a large area or over a very large geographical area. Yes, perfect. Now, when I say network, so network works correctly because the various devices and software follow the rules, right? And those rules, they come in the form of standards and protocols, right? Now, those standards and protocols, what are those? Those are agreements of a particular part of how a network should work, right? I cannot just blatantly say that this is how you will send the data. Anyhow you want, you can send the data. Can I say that? No. Yep. There should be some rules by which I can say yes, that this is the standard of working with network, right? So we'll talk about like later in the session we'll also talk about that what is the TCP IP model, what is OSI model, but right now just for the basics I'm telling that if I'm saying like if it is TCP IP model, right? So it follows some standards, it follows some protocols, right? So the number of standards and protocols, it makes it difficult for the network engineer to think about and work with networks. So the world of networking, it has used several networking models over time. So networking models, what they do, they define a structure and different categories, different layers of standards and protocols. So as new standards and protocols emerge over time, networkers can think of those new details in the context of a working model. Now you can think of a networking model as you think of a set of architectural plan for a building, let's say. Like let's say you want to build a house. So you have an architectural plan that how we will proceed and what are the things we need to do first. Right? So lot of different people work on building your house, like electrician, bricklayers, painters, so on. Right? Now the blueprint, it makes sure that all the different pieces of house work together as a whole. So the people who make networking products and the people who use those products to build their own computer networks, they follow a particular networking model. And that networking model defines rules about how each part of the network should work and how the parts should work together so that entire network functions correctly. So OSI model came 10 years later to TCP IP model, guys. It didn't came before TCP IP, it came 10 years after TCP IP model. Before there was no protocol, there was no standard. There were general standards that were that were different for every vendor, right? So if I am having, let's say, a switch from Cisco, right, or a router from Cisco, right? So I should have the device from Cisco only. My device, Cisco device, can only communicate with the Cisco router. If I have a device from IBM, it won't be able to communicate with the Cisco router because they follow different standards, right? Nowadays we don't know the name of the vendor sometimes of our router, but we have like laptops or computers from different networks, right, or different vendors. So how we are able to do that? Because all my devices, every single device in this world is now using the same model. So if I'm talking about the at the time where standards, they were not same standard was not followed by the people or all the devices, right? So Cisco devices, they are follow the standard they were following, and the Cisco computers, which standard they were following, they both were following the same standard. That's why they were able to communicate with each other. Now all the devices, they are following TCP/IP model. So that's why every device can communicate with every single device, no matter who the vendor is. Now, today the TCP/IP rules as the most persuasive networking model in use, right? So practically every computer operating system in existence of today, from mobile phones to mainframe computers, every network built using any product, either it is Cisco product or any other product, right? They are following TCP/IP model, right? Now, as we started our session with the question that what is a network? So the devices which are communicating with each other all over the world, that is called a network, right? So like if I say that there is LAN, right? LAN stands for local area network, right? There is MAN as well. MAN stands for metropolitan area network. There is WAN as well, right? WAN also comes under TCP/IP networking, and it stands for wide area network. Yes, perfect. So when I'm talking about local area network means the network which we are connected in, like at our homes, right? It can be inside like small office, home office network, we can say. Can I call it Soho network, small office, home office? Yes, correct. So local area network means that it uh, covers a very small area, but it's not that much small. It can be in a room as well, right? Or a building as well, right? So let's say there is a building, it has three floors. On the all the three floors, there is same company's office. So all those things, all those floors, they are connected with each other, right? So that is what? That is also a local area network created, right? Outside that building, the network will not stay local area network. Yep. Then there is MAN, metropolitan area network, right? Now, what can be metropolitan area network, right? How much area it covers, and is it like like in LAN also we are using router. So whatever devices are connected to the router and are inside the router, that is called local area network, right? Metropolitan area, not the full earth. City based connection, can I say? Like some time back we were having like cable TV connections, right? That is metropolitan area network. Now it covers an area of around 50 to 150 kilometers, right? So within a city, the network that is created, that is called metropolitan area network. Now if I say, let's say there are two cities and the network between them or the distance between them is 1500 kilometers or 2000 kilometers. So will that be called a metropolitan area network? If my one branch is in, let's say, city 1, right? So it's in city 1 and second branch is in city 2 and the distance between both of them is 2000 kilometers. Will that be metropolitan area network? No, that won't be metropolitan area network, right? Metropolitan area network maximum 150 kilometers. Within 150 kilometers, if we are communicating, right? So that is man. Perfect. Now, next is WAN, wide area network, right? Now, when I'm talking about wide area network, how much wide it can be? Country to country, right? So, can I say internet is wide area network? So when I'm saying the network in which billions of devices are connected with each other, that is internet with uppercase I, capital I, right? The internet with lowercase I, right? It means two devices communicating with each other, right? So when two devices are communicating with each other inside a room, so internet means PAN, personal area network, right? It is smaller than LAN, right? And it tells that two devices are communicating with each other and it is within a room only. It's not outside a room, within a room only. That is known as internet with lowercase I, right? And the whole www, the World Wide Web, that is internet with uppercase I. Yep, hotspot or Wi-Fi you can also call internet with lowercase I within a network, within a room only. If you are communicating, then only, right? Now, if I'm talking about the wide area network, why I'm giving you all these definitions, why I'm telling you, because further in this course, we'll be discussing more in detail about the wide area networks. Where I will be more talking in terms of local area networks, how Ethernet and local area networks work. So I'm preparing you guys for those things, right? So that's why the first topic I've kept is introduction to TCP/IP networking, right? Now, in this, what happens? There is one thing, right? We all say that internet with uppercase I, the www, right? Internet is wide area network. Mr. Monsuru, we can say within an office or room, right? We are communicating not over the internet. That is lowercase internet. Yes, when you are not talking using the Wi-Fi, internet, Wi-Fi router, anything, that is internet with lowercase I. Perfect. Now, as I'm saying, the wide area network is internet. So if internet is wide area network, then what is GAN, which stands for Global Area Network? Intranet is the connection, or you can say the network, which is only for the organization's internal employees, for the employees of the organization, which they can access. That is intranet, right? That is office network. So let me tell you the difference. Now the thing is, when the devices are communicating with each other, right, all over the world, that is wide area network. But when you add domain names or websites, we can call it, with wide area networks, so it becomes global area network. Yes, got it or not? See, when devices are communicating with each other, like let's say I'm sending you some data, that is over wide area network, right? But if there is any domain in between, a website is in between, let's say I'm through WhatsApp I'm sending the data, so WhatsApp is a domain name, right? So if through a domain I'm sending you the data, that comes under global area network. Yes, without any domain name, if I'm sending data, then it is internet wide area network. But if I'm including the domain name through a website like Facebook, I'm sending you data, Instagram, I'm sending you a message, Gmail, I'm sending you a message. So there is a domain between both of us, which is allowing us to connect, right? Then it becomes global area network. And that's why it's all the part of global area network now, because we are sending the data, all the data through some domain. So these are the types of network. Now in these types of network, we have also heard there is one CAN, and it stands for Campus Area Network. Now what is Campus Area Network, guys? College network. Now, can I say it is within a building? No, I cannot say that it is within a building. Network in universities or schools. Great. So the thing is that there are, let's say, different, it's a campus, right? A university campus. So there are different buildings, right? This is a technical building where technical courses, the people who are uh, pursuing technical courses, they have classes, right? Business management, right? Some medical courses. So all of them, they will be having a common server room, right? So the technical building will be having some devices, right? The business, the people who are learning business, right? So they will also be having some devices. Now medical building will be also having some devices. Now making sure all the devices they are getting proper internet, managing the network of all those devices, and also making sure that every device uses a not unlimited amount of internet, but in campus and universities all the devices they get an amount of network, right? So that amount of network, right, or that amount of internet is managed by the server room. So all these buildings and their devices will be connected with the server room where it will be managed, and server room will be allowing them if you can connect, right? So you should be in the same network, right? So this whole network inside a premises is known as campus area network. Now let's say there is an organization, right? Now that organization, uh, it's having, let's say, different multiple departments, right? There is a marketing department, sales department, then there is a training department, then there is a security department, then admin department, then operations department is there, right? HR department is there. So lots of departments are there, right? If there is a separate network for all of them, a separate LAN, let's say. So I've given a router. To that router only marketing team can connect. I've given a router only sales team can connect. I've given a router only operations team can connect. I've given a router where uh, like any other team can connect, right? Training team can connect. So can I call it a campus area network, or will I call it a local area network? Let me know. Yeah, they have unique login IDs, but all of them they are connected to same network at the end. Yes, and it's not that a different LANs are connecting with each other, right? We have created sub part of the network. Yes, so we have broken down one network into different parts, so that we have given one part of the network to team 1, then other part to team 2, other part to team 3, like that it is. So that is how we are talking about into terms of TCP IP networking. Great. Now when we are talking about TCP IP, like it's been around an hour, right? And we are talking about TCP IP, right? So what TCP IP networking model is, how will we define that? Perfect. Now, when I'm talking about TCP IP networking model, so networking model is sometimes it is also known as networking architecture or networking blueprint, right? So it refers to a set of documents, right? Each document will describe one small function which is required for a network, and collectively these documents they define everything that should happen for a computer network to work. Some documents they define a protocol, right? What is a protocol? A set of rules that device must follow to communicate. Other documents they define some physical requirements for networking. right? Even there are some documents that could define you the voltage and the current levels used on a particular cable when you are transmitting the data, right? So you can think of the networking model as you think of an architectural blueprint for building a house. So you can build a house without the blueprint. Surely, we know that. But the blueprint can make sure that the house has the right foundation and structure so that it will not fall down, and it has the correct hidden spaces to accommodate the plumbing, electricals, the gas, and so on, right? So, also, many people that build the house use the blueprint, right? Electricians, bricklayers, painters, so on. So if they follow the blueprint, their part of the work should not cause problem to other workers. Similarly, like that, you can create or build your own network, write your own software, build your own networking cards, and so on to create a network. But it is much easier to simply buy and use products that already confirm some well-known networking model or blueprint, right? Because the networking product vendors build their products with some networking model in their mind, and their product should work well together, right? That is the meaning of networking model. Now let's understand the TCP/IP. So today the world of networking, it uses one networking model, which is TCP/IP. Now, the world has not always been so simple, right? There was a time when networking protocol didn't exist, including TCP/IP. I'm talking about, right? Vendors, they created the first networking protocols. These protocols supported only that vendors' computers. So, IBM, the computer company, was with the largest market share in many market in 1970s and 80s. They published its system network architecture networking, right, in 1974, right? It was called SNA, right? Systems network architecture networking model, right? So other vendors, they also created their own proprietary networking model. So as a result, if your company bought computer from three vendors, network engineers, they often had to create three different networks based on the networking model created by each company, and then somehow connect those networks. Making the combined network was very complex, right? Great. Now, although vendor defined proprietary networking models, they often worked well. So, having an open vendor neutral networking model would aid competition. So, the International Organization for Standardization, right? The ISO, right? They took on the task to create such model starting as early as the late 1970. So beginning work on what would become known as OSI networking model, right? So 10 years later to like OSI, like TCP/IP, OSI came, right? So they had a noble goal for the OSI model and to standardize the data networking protocols to allow communication among all computer networks across the entire planet. They worked toward this goal with participants from most of the technologically developed nations on earth participating in the process. A second, less formal effort to create an open, vendor neutral, and public networking model sprouted fourth from US Department of Defense contract. So researchers at various universities, they volunteered to help further develop the protocol surrounding the original work, right? And These efforts resulted in competing open networking model called TCP/IP, right? So in 1990s, what happened? Companies they started adding OSI, TCP/IP or both to their networks. But by the end of 1990s, TCP/IP had become the common choice and OSI fell away, right? So in the 21st century, TCP/IP dominates. Proprietary networking models still exist, but they have mostly been discarded in favor of TCP/IP. The OSI model, its development suffered because of a slower formal standardization process as compared with TCP/IP, right? And TCP/IP network model originally created almost like entirely by a bunch of volunteers, and it has become most prolific network model ever, right? Now request for comments is a legal document which tells that how the protocol will work, right? How anything will work, how the data will be transferred. If I'm talking about TCP/IP, so the RFC of TCP/IP, if you read, it's a very lengthy document which tells how the data will transfer, how the acknowledgement will arrive, how the protocols will be used, how they will be choose, right? Like which protocol to use right now, how the path will be found to on which path the data should be sent, right? Everything, right? So the TCP/IP model also avoids repeating work already done by some other standards body or a vendor consortium by simply referring to standards or protocol created by those groups. So, like there is IEEE, the Institute of Electrical and Electronic Engineers. So that it defines Ethernet LANs, right? The TCP/IP model does not define Ethernet and RFC, but it refers to IEEE Ethernet as an option, right? Now the TCP/IP model creates a set of rules, right? And it allows us to take a computer out of the box, plug it in the right cables, turn it on, connect to, and use the network. So you can use a web browser to connect to your favorite website, use most any app, and it all works, right? How? The operating system of the computer implement parts of TCP/IP model. So the Ethernet card or wireless LAN card built into the computer implements some LAN standards which are referenced by TCP/IP model. So vendors that created the hardware and software, they implemented TCP/IP. That's why it is working fine, right? And to help the people understand, right? Every networking model, the whole networking model, each model breaks the function into small categories, right? And those categories are known as layers, right? So the TCP/IP model shows the more common terms and layers used when people talk about TCP/IP today. So the bottom layer focuses on how to transfer bits over each individual link. The data link layer focuses on sending data over one type of physical link. For instance, networks they use different data link protocols for the Ethernet, right? Uh, LANs versus wireless LANs, right? The network layer focuses on delivering data over the entire path from the original sending computer to the final destination computer, right? And top two layers focus more on the applications that need to send and receive the data. Yes. Now you might have also heard of many of the protocols in all the layers, like you might have heard of HTTP. Yes, Post Office Protocol, third version, right? Simple Mail Transfer Protocol, you might have heard, right? In transport layer, there can be TCP or UDP. Yes, then it can be IP or ICMP, right? In internet layer. Now, Ethernet protocol, the Ethernet and 802.11 for Wi-Fi, right? These are the protocols at data link and physical layer. Okay, so if I'm talking about this TCP/IP networking model, right? So in that, what we have at the very top, it is application layer, and we have heard the application layer is the layer which is closest to the user. But we start the counting from the very bottom, right? Like physical layer at the bottom, this is first layer one, then data link layer, layer two, internet layer three. Yes, we have seen that. So if application layer is the layer which is closest to the user, why it's not layer one? There is a computer, right? Now you need to start power on that computer. What is the very first thing you do? You plug it into a power source. Yes or no? See, you plug your computer to a power source, then the power travels, and the last thing after the whole process of the data which happens inside your device, after all the process, you get what? You get the GUI, the window screen. So that means it is the last layer. That's why application layer is known as the last layer. Yes. So first everything is starting from the physical layer, which is I would say yes. Now the very first model, right, or very first layer from the top, right, like layer 5 is application layer. Perfect. Now it provides the services to the application software running on a computer. So the application layer, it is not defining the application itself, but it defines or tells the services that application need. Let's say application protocol is there with the name HTTP, right? So HTTP will tell how web browser can pull the contents of a web page from a web server, right? So if you want something, if you want the page, if you want some information about a course from infosec train, so HTTP knows how to pull that information from the website or web page of infosec train, right? So application layer, it provides interface between the software running on a computer and the network itself, right? And the most popular TCP/IP application today is web browser. Many major software vendors either have already changed or are changing their application software to support access from a web browser, right? And thankfully, using a web browser is easy. You start a web browser on your computer, and select a website by typing the name of the website, and the web page appears in front of you. Yes. So what really happens, right? So to allow web page to appear on your web browser, right? So I'm pasting a picture for making you that understand that, right? Web server Larry and web browser Bob, right? So imagine that Bob opens his browser and his browser has been configured to automatically ask for web server, Larry's default web page, right? Or home page, right? So this is the general way which looks like, right? So Bob said, give me your web page, and Larry said, here is the file home.html, right? What really happened, Bob's initial request actually asked Larry to send his home page back to Bob. Larry's web server software has been configured to know that the default web page is inside a file known as home.html. So Bob receives the file from Larry and it displays the content of file in Bob's browser, right? Now, if you take a closer look, HTTP tells how shows how application can each on each endpoint computer, specifically the web browser application and web server application, they use a TCP/IP application layer protocol to make the request for a web page and return the contents of the web page, right? The applications use HTTP. And when HTTP arrived, around 1990s, right? So HTTP did not exist until there was a person whose name was Tim Berners-Lee. Everyone might have heard of this name. Everyone. So Tim Berners-Lee, he created the first web browser and web server, right? And Berners-Lee, he gave HTTP functionality to ask for the content of web pages, specifically by giving the web browser the ability to request file from the server and giving the server a way to return the content of those files, right? Now a refined image. You all have seen this image. This is a layman's image, right? Now a bit more refined image, let me show you. Now isn't it a bit more refined image? It's telling bit more things. So to get the web page from Larry, Bob sends a message with the HTTP header. So protocols generally they use headers as a place to put information which is used by the protocol. Header has a information and header includes the request to get a file, right? So header will send an information that I want home.html, right? So it sends a request get home.html, right? Now here it sent again the HTTP header okay. Let's say okay is written inside it, and then it says home.html, right? So the message begins with HTTP header with a return code 200, which means something as simple as OK returned in the header. HTTP always defines other return codes so that The server can tell the browser whether the request worked or not, right? Now, the second message also includes the first part of the requested file, the header, right? And another message from web server to Larry. What it is? But this time without an HTTP header. So HTTP transfers the data by sending multiple messages, each with a part of file. Rather than wasting the space by sending repeated HTTP headers, the list the same information will be repeated. So additional messages, they simply omit the header. So no matter how many parts of your data are there and in how many parts it is sent, just the thing is you have this home.htm, right? So in the very first segment or very first part of the data, which is replied back by the server, which server sent back to the web browser, it had the HTTP header, but others others won't be having the header, right? So that the data, more data can be sent, and it does the header does not consumes the space. Clear? So this is an intro about application layer, right? Then there is transport layer. Now, what is transport layer? What is the need of transport layer, guys? Share the package. So many TCP/IP application layer protocols exist, right? And the TCP/IP transport layer, it includes a small number of protocols, two most commonly used, right? TCP and UDP, right? So if I talk about TCP, what TCP is and what UDP is. Okay, so we were talking about the TCP and the UDP, and when we are talking about TCP and UDP, the thing is TCP stands for Transmission Control Protocol because it is uh, connection oriented, it sends acknowledgement, it's reliable. That's why it is slow, right? And when we are talking about UDP, so UDP stands for User Datagram Protocol. It is connectionless because it does not send any acknowledgement. It's non-reliable. It does not assures you that your 100% data will be delivered to the target, and th that's why it is fast. So why you need a protocol which is fast but not non-reliable? Yes. Now, if we talk about the Gmail, yes. We are talking about, let's say, Gmail. Now if you are if you are sending an email to your friend, right, and it uses UDP, so maybe half of your email is dropped, right? So that's why in those places we use TCP, so that we have to make sure that my data is reaching the target. Yep. Now, UDP is something which we are using right now. You can afford packet loss. You can afford that for some time the sound can be lost, right? I'll repeat it again. But can you afford that uh, if my voice, like you are not like you are getting my voice perfectly, but after every word I speak, you are getting a pop-up on your screen. Can you afford that? Correct. Here we are using UDP, right? So these are the two protocols which are used in the transport layer, right? Now, to appreciate what the transport layer protocols do, you must think about the layers above the transport layer, the application layer. Why? Well, each layer provides a service to the layer above it, like error recovery service provided to application layer protocol by TCP. Now, how that error recovery service is given? So let me paste a picture. Now it will be a refined picture of what we learned before, right? In the application layer. Now can you see this image? What is happening? Bob and Larry, both of them, they used HTTP to transfer the home page from web server of Larry to Bob's web browser. Yes, agree? Perfect. Now, what happened? What would have happened if Bob's HTTP GET request has been lost in transit through the TCP IP network? If I am sending a GET request and it is lost, then? Or what would happen if the response that the server is sending to me, which included the contents of the home page, that gets lost? So in both of the cases, what will happen? Bob will not get that web page in his browser, right? So TCP IP, it needs a mechanism to guarantee the delivery of data across the networks, because many application layer protocols want a way to guarantee the delivery of data across a network, right? So the creators of TCP, they included error recovery feature, right, to recover from errors. So TCP uses the concept of acknowledgements, right? So when Larry is sending a web page to Bob in three steps, three parts, right? Sequence 1, sequence 2, sequence 3 is written, right? So there is sequence number in each message. So the network has a problem and the network fails to deliver the TCP packet with sequence number 2. Here we can see that, right? So Bob realizes that message 2 was lost. That realization by Bob's TCP logic causes Bob to send a TCP segment back to Larry to send message 2 again, right? So Bob found that I received packet number sequence number 1 and sequence number 3, but sequence number 2 I don't have. So Bob's browser will ask the server that send the sequence number 2 back. I have not received it. Perfect. Now the next layer that we have is network layer. Share the package on IP address. Great. So the application layer include many protocols. The transport layer includes fewer protocols, the TCP and UDP only. The network layer includes a small number of protocols, but only one major protocol, which is IP, right? What is the name? Internet Protocol. Yes. In fact, the name TCP/IP is simply the name of two most common protocols, TCP and IP, right? So IP provides many features like addressing and routing, most common things, right? Now, what is Internet Protocol? Imagine you just wrote two letters, one to a friend on the other side of the country and one to a friend on the other side of town. So you address the envelopes and put on the stamps. So both are ready to give to the postal service. Is there much difference in how you treat each letter? Not really, right? So typically you would just put them in a same mailbox and expect the postal service to deliver both letters. Yes. Now the postal service must think about each letter separately. You don't have to think. The main agenda for you is just write the letters and write the address and post it, right? Now, postal service will have to think about each letter, then make a decision where to send each letter so that it is delivered, right? So for the letter which is sent, which should be sent across the town, the people in the local post office probably just need to put that letter in another truck, right? And the letter that needs to go across the country, the postal service sends the letter to another post office, then another, and so on until the letter gets delivered across the country. At each post office, the postal service must process the letter and choose where to send it next, right? And to make all these things work, the postal service they have regular routes for small trucks, large trucks, planes, boats, and everything to move the letters between postal service sites, right? Now the service must be able to receive and forward the letter, and it must make a good decision about where to send each letter next. Now consider the difference between the person sending the letter and the work that the postal service does. So the person sending the letters expect the postal service will deliver the letter most of the time. The person sending the letter does not need to know the details of exactly what path the letter will take, right? And in contrast of that, the postal service does not need to create the letter, but it accepts the letter from the customer. Then postal service must know the details about address and postal code that group addresses into larger groups, and it must have the ability to deliver the letters. So the TCP/IP application and transport layers, they act like the person sending letters through the postal service. And these upper layers, they work the same way regardless of whether the endpoint host computer are on the same network or are separated by the whole internet, right? To send message, the upper layer asks the layer below them, the network layer, to deliver the message, right? And the lower layers of the TCP/IP model, they act more like postal service to deliver those messages to correct destination, right? And to do that, these lower layers must understand the underlying physical network, because they must choose how to best deliver the data from one device to another, right? So what does this all matter in networking? The network layer of TCP/IP networking model, it is defined by internet protocol, right? It works much like a postal service. IP, or internet protocol, it defines the each computer should have a different IP address, just as the postal service defines addressing that allows unique address for each house, each apartment, each business. Similarly, IP defines the process of routing, so that devices called routers, they can work like the post office. So forwarding data, packets of data, so that they are delivered to the correct destinations, right? So whenever we send data, how we are sending from my device, it went to my router, from my router to another router, then from that router to the next router, it hops, the data hops, right? And just as the postal service created the infrastructure to deliver letters, post offices, sorting machines, trucks, planes, and personnel, right? The network layer defines the details of how a network infrastructure should be created so that the network can deliver the data to all the computers in the world, right? So this is the work of network layer, right? Next is TCP/IP data link and physical layers. Now, the data link and physical layer that define the protocol and hardware required to deliver data, right, across some physical network. So these two layers, they work together quite closely. In fact, some standards define both the data link and physical layer functions. Physical layer defines the cabling and energy, like electrical signals, that flow over the cables. Some rules and convention exist when sending data over the cables, are there, right? So those rules exist in the data link layer of the TCP/IP model. Now focusing on the data link layer for a moment. Just like every layer in in this model that we have learned, data link layer, it provides services to the layer above it in the model, like network layer. So when a host or router's IP address chooses to send an IP packet to another router or host, That host or router then uses link layer details to send that packet to next host or router. That means the MAC address. Because each layer provides service to the layer and to the layer above it. Yes. Now think about IP logic, right? Same example I'm taking, right? Larry and Bob. Now this is the thing, right? So Larry's IP logic chooses to send the IP packet to nearby router, right? So there is like we can see there is a simple line between the Larry's and router 1. So that drawing means that some Ethernet LAN sits between both of these, right? Now we can see four steps of what occur at link layer to allow Larry to send the data. So first it was IP packet which was encapsulated with Ethernet header and Ethernet trailer was added, right? So Larry encapsulates the IP packet between the Ethernet header and trailer, which creates an Ethernet frame. Then Larry physically transmits the bits of Ethernet frame using electricity flowing over the Ethernet cabling. Router, the name let's say is R1, so it receives the electrical signal over the cable and recreates the same bits by interpreting the meaning of electrical signals, right? Then the router de-encapsulates the IP packet from the Ethernet frame by moving and discarding the Ethernet header and trailer. Yes. So by the end of this process, Larry and router 1 have worked together to deliver the packet from Larry to router 1. Now, we discussed about the different layers, right? That what every layer does, right? What is the work of every layer, right? Now, when we are talking about the next thing, right? So, can we just do one thing that let's say we are comparing the OSI model and TCP/IP model when we are comparing that. So what we can get in that? Like what is the difference, main difference between TCP/IP model and OSI model? The thing is, OSI model has 7 layers, TCP/IP model has 5 layers, right? Apart from that, why we are not using OSI model and why we are using TCP/IP model? So whenever there is a problem in your organization, right? There is some problem with the, yeah, it's a blueprint. But in OSI model, all the layers they are separate. So it's easier to understand the working, how the network is working, how the data is getting transmitted. So whenever troubleshooting happens, right, in which layer the problem exists, that is found using OSI model, isn't it? We cannot find it using the TCP/IP model. Now, the next thing is the IP routing, right? So there is a part of IP routing, right? So in IP routing, what happens? Network layer provides a service for forwarding the IP packets from one device to another, right? And any device with an IP address can connect to the TCP/IP network and send packets. Yes. Now in this figure, if you can see, right? Same Larry and Bob are there, the two people, right? Now, web server Larry wants to send part of a web page to Bob, but now with details related to IP, right? So here, if you can see, Larry, it has a familiar application data, HTTP header, TCP header, ready to send, right? In addition, the message now contains an IP header. The IP includes a source IP of Larry address and destination IP of Bob's IP address. Yes, right? So Larry is ready to send an IP packet. Larry's IP process chooses to send the packet to some router, a nearby router on the same local area network, right? Okay. So Larry is ready with the IP header, the TCP header, and the TCP information, and the HTTP information, the web page information. In the IP information, there is the IP address of the target whom I want to send the data, and there is source, right? Who sent the data, right? So Larry is ready to send the data, and Larry's device or Larry's web server chooses a router which is in the same LAN to send the data with the expectation that router will know how to forward the packet, right? Now Larry doesn't need to know anything more about the topology or the other routers or anything, right? Now router 1, let's say, receives the data, right? This router 1 receives the IP packet, and router 1's IP process makes a decision, right? Because it looks at the destination address, it compares the address to its known IP routes, the path, right? And it chooses to forward the packet to router 2, right? Instead of router 3, right? Now this process of forwarding the IP packet is known as IP routing or routing, right? Now router 2 does what? It repeats the same kind of logic used by router 1. So router 2's IP process will compare the packet's destination IP address to router 2's known IP route or IP path and makes a choice to forward the packet to the right, directly to Bob, right? So that is how the routing works. Now inside these routers there is a table which is known as IP routing table, right? Now that IP routing table is having the path for everyone. Yep. And that's how on the basis of that IP routing table, it makes the decision that yes, we have to send the data forward and in to which router. So that's how in IP routing the path is decided, right? We'll discuss that more in detail when we will be covering the routing paths and how the routing happens, right? Now next is data link and physical layers, right? We know how the data is encapsulated and de-encapsulated, right? So Larry here is doing what? Larry is encapsulating the IP packet between Ethernet header and trailer. It creates a frame, right? That frame is called encapsulated frame, right? Then it is physically transmitted bit by bit using electricity flowing over the cable, and router 1 physically receives those electrical signal over the cable. Then it recreates the same bits by interpreting the meaning of electrical signals, right? and it de-encapsulates the IP packet from the Ethernet frame by removing and discarding the header that was added and the trailer that was added, right? And in the end, router 1 has the IP packet only, which it forwards to the target. Now, next is we have the OSI networking model and terminology, right? Correct. So it stands for Open Systems Interconnection Model, right? So at one point in the history, right, of the OSI model, many people thought that OSI will win the battle of the networking model, as we discussed it earlier. So if that had occurred, instead of running TCP IP on every computer in the world, those computers would be running OSI model, right? Now OSI didn't win that battle. OSI no longer exists as a networking model, right? So although some of the original protocols referenced by the OSI model still exist. So why OSI is even there, why we are learning that OSI model. So during those years in which many people thought the OSI model would become commonplace in the world of networking, many vendors and protocol documents started using terminology from OSI model. So the terminology remains today, right? So while you never need to work with a computer that uses an OSI to understand modern networking terminology, you need to understand something about OSI, right? Now, when we compare TCP IP model and OSI model, right? So on the right hand side, you can see TCP IP model, right? And there is on the left hand side the OSI model. The functions generally match as well. So for the purpose of discussing networking and reading networking documents, think of the bottom four layers as equivalent in name, number, and meaning, right? Even though the world uses TCP/IP today rather than OSI, we tend to use the numbering from the OSI layer. For instance, when we are referring to application layer protocol in a TCP/IP network, the world still says it is a layer 7 protocol, isn't it? Also, while TCP/IP includes more functions at its application layer, OSI breaks those into session layer, presentation layer, application layer, right? Most of the time, no one cares about the distinction. So you will see references like layer 5 to 7 protocols, again using OSI numbering, right? Now, when we are talking about OSI model, right, or TCP/IP model, right? So there is data encapsulation terminology, right? These terminologies are still used. They're still going on, right? Now what happens? Let me tell you first the layers about the OSI model, right? These are the 7 layers, right? Now the application layer, generally it's the GUI. This is the closest layer, closest to the user, and this is the layer which can be seen by the user where the user works. Yes. Now, next layer is presentation layer, and the main work of presentation layer is to encrypt or decrypt the data. Now, apart from encrypting and decrypting, it also does the compression of the data. Now, why the compression of data is needed when I'm sending the data to someone? Anyone? For fast delivery. So the thing is, if the data is not compressed, so the bandwidth will be used more, right? If I am compressing the data, so less bandwidth will be used, and in less bandwidth I will be able to send more data, right? That is the use of compression. Then conversion of data also happens in the presentation layer. Do you guys know that? Okay, so the thing is that when we are talking about the data, right? So data, when I'm sending data, data crosses every single layer. Data goes through every single layer, right? So I'm converting the data into a format which is understandable by other layers. Yes. So that other layers can also understand the data. They do. If you are sending a message to your friend which is hello, right? So these session layers, transport layer, they cannot understand hello, right? We have to convert it into a format so that they can understand which is the data, right? So that's why we have presentation layer. Then we have session layer, right? Session layer does the session management, right? So session management means when the session will be started, if the session is going on smoothly or not, and when the session will be terminated. All those things will be checked by the session layer. Does transport layer perform segmentation? Yes, it takes care of ports as well, right? So that's why it's written here. This is the PDU of transport layer, right? In the 7, 6, and 5th layer, it is called data. Then, when it is segmented, when it is broken into smaller chunks, so the protocol data unit is segment, right? We call it the segment. Then it also takes care of port according to TCP and UDP, whether to use TCP for sending the data or UDP, right? According to the communication that is happening. Then comes the network layer. Now, network layer takes care of the routing as we discussed and the IP addresses. So it adds the packet header, right? That means the source IP and destination IP will be added. Who is sending and where to send. So this whole thing, this protocol data unit for network layer becomes packet. It is called packet here, right? Now after this, it goes to the packet goes to data link layer. Now data link layer works with the MAC address and error control, right? Everyone knows MAC address, media access control address. This is the physical address of your device, right? That means if I'm sending a letter to you and you are living, let's say, in London, right? So if I'm writing, let's say, the name Salahuddin London, will that letter ever reach to Mr. Salahuddin? No, right? I should know his physical address. The London is his network. In this network he is in. So that is the IP address. Yes, that's his IP address. Now I should know the house number, the street, everything to make that letter reach to him, right? So that is MAC address, the physical address of this device. And exactly this is the address of your network interface card, right? Then it takes care of error control. Now MAC address, so in frame header, it adds destination MAC and source MAC address. The device who is sending the data, the MAC address of that device, and to whom I'm sending the data, that MAC address, right? So destination MAC address, source MAC address, destination IP and source IP is added, and in data link layer, a frame trailer is added. Frame trailer is used for error control. Now it is called FCS. FCS stands for frame check sequence, right? Now inside frame check sequence, there are different algorithms that work. Now sometimes it is CRC, cyclic redundancy check. Sometimes it is sums, right? Sometimes it is parity check, right? So it depends, right? What things are working. Clear? Now, what happens exactly inside it? What I did, I just have a formula, let's say. So there is a complex formula that I calculated using all the values, and after calculating it in the trailer, I put the complex formula and its output, let's say 15, the answer, right? So the formula was x plus y square plus c equals to 15, right? So the output of this is 15. So the both the formula and the output I have put inside frame trailer, right, in the FCS, right? That's what happened in error check, right? Error control. So when this frame will reach the target, the receiver whom we are sending the data. So at the data link layer of the target, what will happen? The data link layer of the receiver will also calculate the output from this formula. And if the output of the receiver is 15, right? That means if it is same as the output which sender has sent, then the data was not tampered during the transit. It was not changed during the transit. Otherwise, if it is something else apart from 15, let's say, right? If it is 16, let's say, right? So that means there was some change made to the data. So it is not authentic and it is not the correct data. So the data will be dropped, right? The frame will be dropped. So that's how your frame check sequence and the error control happens, right? And after that, there is physical layer. So physical, here, this whole thing in like data link layer, it's called frame, right? Then after when frame is sent to the physical layer, the frame is converted into bit format, zeros or ones, right? So after converting it to the 0 and 1, then it is sent to the physical layer of the receiver. Now when receiver receives this data, right, what happens? First, receiver, physical layer of the receiver converts the data into a format so that other layers can understand, right? Then the data, the frame goes to the data link layer. Now the data link layer checks the destination MAC address and source MAC address. If the destination MAC address written in the frame matches to me or not, right? If it is matching, right, then this frame header is shredded, it's removed, and then it checks the value of FCS. So it calculates the output. If the output matches the same as sender has sent, so it will shred this frame trailer as well. So we are left with packet, and that packet is forwarded to the network layer. Now network layer checks the source IP and destination IP. What is the source IP written? What is the destination IP written? Right? If the destination IP matches, right, then it will remove this packet header also. Clear? Now once it removes those packet headers, right? We are left with the data that we are sent, and that data is sent to the transport layer, right? That's how this thing works.